Let's take a look at linear and angular momentum, where linear momentum we defined as g is mv, and it's a vector value, so direction's important here. So if we have a small mass m that's moving with a velocity v, we know that its momentum vector will be in the same direction, g. It'll be m times v. And since v can be broken up into components, we call this theta, we can also break up g in a similar fashion. So gx would be mv sine of theta, where v sine of theta is really vx here, and gy would be mv cos of theta in this direction. So the vector nature of linear momentum allows us to do that. If we want to talk about angular momentum, h, it's defined as r cross g. It's the distance from some reference point O, in this case, to the momentum vector g. So for us, h, which is also a vector, will be r cross mv. And the cross product here guarantees that these things are perpendicular to each other. We also know that the cross product can be done as r mv sine of theta, where this angle is the angle between r and g, which if we look over here is that angle right there. Here's r hat, here's g hat, if you want to call it that, and that would be the angle between r and g. So we find that h in this case will be r mv sine of theta, or r mv perpendicular, to remind us that it has to be the velocity component that's perpendicular to r. And the direction is given by the right-hand rule, where in this case it's rotating this way with some omega, as this velocity here carries that. And the right-hand rule says that it would be out of the board, so out of the screen. If we were working in an x, y, z frame, it would be in the k-hat direction in this case. And it's perpendicular to both r and to v. We can also define this using angular velocity terms, where r is sweeping along at a rate of omega radians per second, and as such the velocity here perpendicular would be r omega at that instant, and we can put that into here and we'll get that h is equal to r m times r omega, or m r squared omega. Now this r squared here is important. That's the mass moment of inertia, I. And recall that the I of a concentrated mass is simply mr squared. If we had other shapes here that we were working from, the I of a hoop is also mr squared. The I of a disk, if we're rotating it, is 1/2 mr squared. The I of a bar, if rotated, has a few values. Here about the center, it will be 1/12 ml squared. If we rotated it about the end, it's 1/3 ml squared. And also the parallel axes theorem is also very useful, where I about any axis is I about the centroidal axis plus m offset distance squared. And this must be the centroidal axis. And with this family of equations, we can generally solve for the I of any shape. And all those values are useful because we can also write the angular momentum in terms of the angular velocity, I omega. And still, it's a vector quantity, direction given by right-hand rule. In this case, it's the direction that omega is going. The angular impulse and momentum theorem states that the angular impulse, the integral of m dt, if you have an angular impulse, it will cause a change in angular momentum, which we can find as h final minus h initial. And that's our angular impulse. So any case where we have a moment applied to a system while it's undergoing some type of a collision, we would not expect the angular momentum to be conserved. Over here we have a mass that's colliding with a long hanging bar here, and that collision would conserve angular momentum. If we look at the whole system here, there is no external moment values being applied, in which case, so if sum of all the m externally applied is equal to 0, delta h is equal to 0, h final equals h initial, and the angular momentum is conserved. Let's say that this bar was being driven by a moment or torque, same thing in this case, while this collision takes place. That would be a very large external moment, and we would not expect it to conserve angular momentum. This torque is going to continue to drive it through. Now that's different than if it was freely rotating with some omega. If it's rotating with some omega, that's not a torque or a moment, and that would conserve angular momentum. But if this thing were connected to some type of a motor that were driving it, then we would not expect it to conserve angular momentum. As an example, let's have a small mass m collide with a free hanging bar of mass capital M and length L, and let's have the small mass become embedded inside of the bar. Let's give it an initial velocity of v0 on impact, and let's find omega final, the angular velocity of the bar after this impact. If we look at it, we have a mixture of linear momenta coming in here and angular momentum as well, which is fine. First, we can break down v0 into a vx and a vy value. And let's call this angle theta here between the bar and the velocity. So vx will be v sine of theta, and vy will be v cosine of theta. And let's call these sub-zero. They're the initial values. In the y direction, we have no rotational effects, so this is all a linear momentum problem. G, y, the mvy0. And since the bar is pinned at the top at O, it can't move, and G final would be 0, so there's going to be an impulse in the y of G final minus G initial, which would be 0 minus mv0 cosine of theta, and that would be the impulse. Now regarding the sign here, by leaving these values over here positive, we are saying that down is positive, and this will be positive x for this problem, which is fine. We can do that. So there's an impulse on the small mass in this direction. which is what stops it from moving when it becomes embedded inside of the bar. So there's an impulse generated in the y direction, but there's no momentum or angular momentum events after that. In the x direction, we have a perfectly plastic collision where they stick together. And we know that these types of collisions will conserve angular momentum. They will lose kinetic energy, though. So we do not expect this to conserve kinetic energy. So our angular momentum equation will be the sum of all the angular momentum before the event is equal to the sum of all the angular momentums after the event. There's no external moments or torques here, so it's conservative. And before the event, we only have Vx, so that'll be L, small l is our length, mv. And then after, this would be Vx, 0. And then after, we're still going to have LMV x, except now it's a prime. It's stuck inside of here, and it'll be moving with some new velocity, v. Plus the bar itself could be rotating, which would be I omega. And this would be I of the bar and omega of the bar. So there's our conservation of angular momentum equation. Now our Vx here, it's embedded in the bar over here. So that velocity, Vx prime, will be L omega. So Vx prime is L omega. And we'll get LMVx0 is Lm squared omega plus IL omega, which becomes omega IL plus ML squared. And if you think about it, that's the I of the bar, and that's the I of the small mass, and this is really I total of the bar with a mass embedded in it as it rotates. So that's what that's telling us. And from here we can now solve for omega. Omega final will be LMV 0 sine of theta over IL plus ML squared. That's the angular speed that the bar and ball would move away with. And note that only Vx initiates this motion. In the y direction, that motion and that momentum is lost to the system. Here we have the same mass striking a long bar of length L, elastically this time, and it rebounds off. And we're asked to find omega final for the bar and theta final, the rebound angle for the small mass. We can start by breaking things up into components. And here we have V0, which we know we can make a Vy from that, and a Vx. And if that's theta here, this is theta over here as well. And Vx 0 will be V0 sine of theta. And Vy0 will be V0 cosine of theta. And we can see here that Vy0, if it rebounds, will just continue. There's no forces in that direction to slow it down. There's no friction. So Vy final will be the same as Vy initial. What could happen here, though, is the rebounding of Vx. The rebound speed for Vx will probably be less than the impact speed because this bar can move during that impact. So that will change the angle, the reflection angle here, as this leaves. So this will be an elastic event. which tells us that it's going to conserve energy as well as momentum. And we'll start with our angular momentum statement. The sum of the angular momentum before the impact equals the sum of the angular momentums after the impact. And before the impact, we really just have Vx. And we saw that its angular momentum will be L mvx 0. Then after the impact, it'll be L mvx. We'll just call it x without the 0, plus I omega of the bar, which I'll call L for the length of the bar. And let's clean this up a tiny bit. I'll divide through by L on M. And we'll get equation for Vx prime here. Vx after will be Vx before minus I omega on Lm. So that's a way of finding the rebound speed, and I'm guessing that it's positive initially, and I'll let the equations tell me when it becomes negative. Next we'll apply conservation of energy. So the sum of all the kinetic energies before should equal the sum of the kinetic energies after. And we have an interesting event over here. If we take a look at this for a second, we have V0 coming in, and we know that it has a Vy and a Vx. So the kinetic energy is 1/2 m V0 squared, which is 1/2 m. Now V0 squared by the Pythagorean theorem would be Vx squared plus Vy squared, which tells us we can break this apart into 1/2 mvx squared plus 1/2 mvy squared. Now we can do that because they're squared. Our kinetic energy equation will be 1/2 mv0x squared plus 1/2 mv0y squared as the before energy. And then after, we'll have 1/2 mvx squared, where that's the prime after, plus 1/2 mvy squared plus 1/2 I omega squared, where that's the I of the bar, and the I of the bar is 1/3 ml squared. In this case, it's a bar spun about its end. Where here we know that V0y and Vy final are the same, so these two terms will subtract out. The y-axis isn't bringing any energy changes to the system. Cleaning it up a little, we can multiply through by 2. And divide through by m as well, just to collect all the terms over to here. And we'll get that V0 x squared is equal to Vx squared plus IL omega squared on m. And we have the solution for Vx prime here already. We can plug this in and square that. So doing that, this will become V0x squared is equal to this squared, which is all of this here, Vx0 squared minus 2 Vx0 omega f on Lm plus I omega on Lm all squared. And then we still have this term here, so plus I omega squared on m. Now looking at this, we have the same two terms here on both sides, so we can cancel these out, and that'll leave this equal to 0. So if I bring this to the other side, we'll get 2 Vx0 0 I omega on Lm equals I squared omega squared over L squared m squared, if we bring that square in, plus I omega squared over m. Now to clean this up a bit, we can divide through by an I. That'll get rid of that and that. We can divide through by one of the omegas. We can multiply through by L squared m squared, and that'll leave an Lm up here. That'll get rid of that one entirely, and that'll leave an L squared m over here, and this one will cancel out. So here we get 2Lm Vx0 is equal to I omega plus ml squared omega, where we can factor omega out here, and we'll get I plus ml squared, where once again there's our I total we see. And with that we can solve for omega. Omega final will be 2Lm Vx0 divided by that, which is I plus ml squared, where again I of the bar is 1/3 ml squared. We'll just leave that as I for now though. And this is interesting. In here, Lm Vx0 is hx0, the initial angular momentum that we had coming into the event. So this becomes 2h0 on I total, which is sort of interesting. That gives us our answer for omega final, which we can now plug into here and solve for Vx prime, which we can then use to find theta final. So Vx prime will be Vx0 minus I over Lm times all of this. 2 Lm Vx0 over I plus ml squared. And this Lm will cancel with that Lm. And we have a common term of Vx0 here, so we can pull that out in front as 1 minus 2I over I plus ml squared. And let's make a common denominator here of I plus ml squared over I plus ml squared, and this will clean up and become V0 I plus ml squared minus 2I all over I plus ml squared. And this I minus 2I gives us a very interesting little answer here. We get that Vx prime is V0 ml squared minus IL over ml squared plus IL. These are still x zeros here and here. And if we look at this in terms of its effect on the problem, if ml squared is greater than IL, Vx prime will be in that direction. If ml squared is less than IL, Vx prime will rebound in this direction. So the value of ml squared, the I of the small mass coming in the x direction versus the I of the bar that's hanging there, drives whether or not the rebound would take place or whether the velocity would be moving in the other direction. In either case, they're subtractive, and we expect that Vx prime will be less than Vx0, which tells us this angle theta up here, final, will be less than theta 0. All right, one last step then is to find this angle theta final. To find theta final, let's look at this rebound event. So the ball comes in and rebounds off, and here's the new velocity, v prime, and it has components of vy 0. We know that that didn't change. And then here's the one we just found, our vx prime, and there's theta final. So the tan of theta final will be the opposite over the adjacent. And here we have our equation for vx prime. In fact, this was v0 sine of theta 0. So we can include that as well. And we'll get v0 sine of theta 0 times ml squared minus il, ml squared plus il, over v0 cosine of theta, which was how we found vy0. And interestingly enough, the v0's drop out here. Sine over cosine is tangent, so we get tan of theta final will be the tangent of theta original times ml squared minus il over ml squared plus il. This term right here is rather interesting. If we think about it, it's delta I over I total. The difference of the i's involved the impact divided by the total i's of the impacts, and it's unitless. And it's sort of a fascinating modifier. Also interesting, in general, we'd expect IL to be bigger than ML squared. The bat ought to have a lot more moment of inertia than the small mass that's coming in. So in general, this equation will work out to be negative Vx prime, which means it's a rebound. However, in the unusual case that ML squared is than I, we get a positive. It'll come in an impact and it'll slow down, but it'll still be moving that way. And we end up with a negative angle, which makes sense as well. It would tell us that the angle of rebound is actually this direction. So this would be a negative theta final, and this side is our positive theta final, the side that we expect it to be on. Thanks for watching.